if you are doing well. My name is Shriya Bansal, and now in this video, we are going to talk about the concept of deadlock avoidance. In the previous video, we have already talked about deadlock prevention. Now in this video, we'll talk about how does the concept of deadlock avoidance work. So this approach to the deadlock problem basically anticipates deadlock before it actually occurs. So the idea is that before the deadlock actually happens, instead of having a deadlock and then taking recovery from it, try to see if you can anticipate if deadlocks are going to happen or not. So in this approach, we actually take care of an algorithm which access or takes care of the possibility that a deadlock can occur, okay, and then it acts on it accordingly. Okay, if the necessary conditions for a deadlock are in place, it is actually still possible to avoid deadlock by being careful how you allocate the resources. Okay, so for that, it employs or takes care of the most famous deadlock avoidance algorithm, that is Banker's algorithm. And trust me, it is actually the heart of what deadlock avoidance really is. Okay. First, let's talk a little bit about safe and unsafe states. So a system is said to be in a safe state if there is a safe execution sequence. Okay, a state is said to be safe if the system can allocate resources to each process in some order and it can avoid deadlock. Okay, formally, we can say that a system is in safe state only if there is a safe sequence. Okay, so a safe state is not a deadlock stage, and conversely a deadlock state means a unsafe state. Okay, an execution sequence is an ordering, okay, for process execution such that each process run till its terminate or blocked and all the requests for resources are immediately granted if the resource is available. Whereas a system is said to be in an unsafe state if there is no safe execution sequence. An unsafe state may not be deadlock, may be deadlock. That way you can see that this region for unsafe is very big, but deadlock inside it is very small. So an unsafe state does not mean that there has to be a deadlock, okay? But it means that there is at least one sequence of request from the processes that you're currently doing that can make the system deadlock. That means an unsafe state can lead to a deadlock state, okay? That's what the overall idea is over here. And to tackle that, right, we basically take care of the Banker's algorithm, which comes really handy over here. Okay, so what we will have is we'll basically have like a resource allocation type of like a system, and then we'll understand the Banker's algorithm. First, let's take an introduction. So the Banker's algorithm, right, is basically a resource allocation and deadlock avoidance algorithm. Okay, which was developed by Edgar Dijkstra that test for the safety by simulating, kind of like an allocated of predetermined maximum possible amount of resources. So it basically latches on upon the idea that it kind of predetermines what's the maximum possible amount of resources, right? And then it makes a safe state to check and to test for the possibility of deadlock conditions for that from all the pending activities, and before actually making the decision whether the allocation should be allowed to continue or not. Okay, so Banker algorithm is called so because this algorithm is used in banking actual systems to determine whether a loan should be granted or not. So you've like big banks, right, who offer loans, but before that they do some calculations. They basically analyze whether you can repay the loan or not. So they actually use the Banker algorithm for that. Hence the name Banker's algorithm. Okay. For example, let's say there are n account holders, okay, in a bank, and the sum of the money in all of their account is X. You add up just the money of all those people in their account is X, okay? And every time a loan has to be granted by the bank, it basically subtracts the loan amount from the total money it has. Let's say by adding up all the account holders' money, I have 100 rupees and someone basically requested for 10 rupees. Okay. So what happens is, since someone took a loan from me for 10 rupees, I still have 90 rupees left. Okay. Then it basically checks, right, if that difference, right, that 90 rupees is greater than S or not. Okay. Now it is done because only then the bank would have enough money, even if all the account holders withdraw all their money at once, still the bank would have enough money, right, to give away the amount or not. Okay, so it's like, think of it like this. Just to give you an example, let's say bank has some X amount, okay, which is, let's say, 20 rupees. And here for all N accounts, the total money comes out to be 100 rupees, okay. And someone basically came and asked for a loan of 40 rupees, okay. Now let's say the bank had a total of what? 120 rupees, right? And someone came and asked for 40 rupees, okay. So that means bank only has 80 rupees left, correct? If the bank does give the loan, the bank only has 80 rupees left. But what if all of these account holders take away their money? Now they will take away 100 rupees, but the bank only has 80 rupees to give. So the bank cannot give it, okay. Only when the amount of the loan required is less than or equal, okay, to the difference of the money bank has minus the money in the account holder. So technically the bank can only give away 100, okay, 120 minus 100, which is 20 rupees, right? Because if it gives more than that, and if all people come on a same day and withdraw their money, the bank will not be able to give back all the amount because it gave away a good amount of money on loan. Okay, so that's what, like, a very simplistic way how the banker algorithms really work. Okay, so for banker algorithm, right, here you have to make sure that you know three things. Okay, you should know, first of all, how much of each resource could possibly be requested by every process. So it's not like every process can request for 10 million resources. It's not possible. Every resource or every process could only request for a particular limit of resources. So you need to know that number. How much of each resource is currently holded by every process, right? How much resources every process are currently holding at any point of time, you need to know that as well. And how much of each resource, okay, the system has available, right? So how much of the resources are currently being holded, how much of the resources are available, and how much of the resources could actually be requested. Okay, you need to know all of the three things at all point of time when you're applying the banker's algorithm. Okay, so always remember that this condition is extremely important, that the resources may be allocated to a process only if it satisfies the condition first. The number of requests that is made is less than or equal to max. Okay, that means the number of requests that has been made by a process should be less than or equal to the maximum number of resources are available. Okay, well, else what will happen is else you have to set error, okay, as the process has crossed, okay, a maximum claim that was made by it. The second thing is that the request should be less than or equal to available. Okay, that means the requested amount should always be less than or equal to the available amount of resources. Otherwise, the process will wait until the resources are available. Okay, it's like, the first point is the process initially said that it will only ask for 10 resources, but now it came in the future and asked for 50 resources. That's wrong, right? You have to set error on that, saying that you have made all your claims for 10 resources. Now you cannot claim more than that. Okay, the second thing is you only have 10 resources available and some process is asking for 30 resources. Again, you cannot do that allocation, right? Because you do not have that many resources. In that situation also, the process has to wait. And only when these two conditions are satisfied, that the requested resource is less than equal to the maximum claimed resource, and second is that the requested resource is less than or equal to the available resource, in only these two conditions, when satisfied, we allocate the resources. Okay, so what you can do is you can think of it like this. We are going to introduce three terminologies over here: available, max, and allocation. So we are going to use some data structures which will implement this. So assume that there are n processes in the system and m resource type. Okay, so here we have So here, let's say we have the banker's algorithm, and here what we have is there are n processes and there are m resources. Okay, now here we need the three data structures: available, max, and allocation. Okay, let's take a look at them. So this is available a vector of length m, which is equal to the number of resources that indicates the number of available resources of every type. You can have resource R1, R2, R3, Rm, and you have to know what all are the quantities available for every resource. What are instances are available for every resource. Okay. So if I do something like this for this available vector, or you can think of it like an array, j equal to k. Okay, that basically means, right, that for the resource rj, k instances are available. For the resource rj, k instances are available. I'll move this down. Okay, so the next one that we have is max. Okay, so max is basically a m cross n matrix which defines the maximum demand of every resource. Okay, so if I do max of I of j equal to k, that means that the process P1, okay, may request a maximum of k instances of resource rj. Okay, so here first of all it's a m cross n matrix. And if I do max of I comma j equal to k, okay, that this means that process pi can request for a maximum of k resources of resource rj. So it's like a 2D matrix where the rows are for processes and the columns are for resources. Okay, and every value define that for this process, for this resource, what's the maximum number of resource that can be allocated. Okay, here we have allocation. Next, again, allocation is a n cross m matrix which defines the number of resource which has already been allocated to every process. So maximum is the maximum you can ask for. Allocation is how much of it has already been allocated. So if I do allocation of I comma j equal to k, it means that for the process pi, it is currently being allocated k instances of resource rj. Okay. So if I think of this over here, in terms of allocation, it is again a m cross n matrix, whereas this was a n length vector. Here, if I do allocation of I comma j equal to k, that means that process pi is currently holding k instances of resource rj. Okay, that's what it basically means, right? Now there is another one which is need over here. Okay, the need is again a n cross m matrix which indicates the remaining resource need of every process. For example, a resource basically claimed for 10 resources. It asked for 10 resources maximum. It currently had 4 resources, so it still need 6 resources, right? So this need matrix basically indicates the remaining need of every process. Okay, so if I do need of I comma j equal to k, then the process pi need k more instances of resource ri, okay, rj, to basically complete its task. Okay, here it's ri, but that means it's rj. Okay, note that the need of I comma j is whatever you need should be equal to whatever you asked for minus what has already been allocated. Correct? That makes sense as well. Whatever you need is always equal to whatever is the maximum you asked for and what has already been allocated. Okay, and trust me, these data structures vary a lot, right, over time with their size and with their values and as the process allocation goes on. Okay, so I'll add the need part as well, which is the fourth one. Need one is very easy to add. In fact, all of them are. So if I do need of I comma j equal to k, right, that means process pi need k more instances of resource rj, and always need of I comma j is equal to max of I comma j, the maximum you asked for, minus what has already been allocated. Okay, that's what the overall idea is, right? And the vector that we took of allocation of I basically represents what all resources are currently, like I would say, allocated to any particular process. Okay, and the vector need I basically represents the additional resources that a process pi may still request to complete the task. Basically the above point itself, I think it's allocation of I comma j and something like that. It's written, I think it basically got misintended over here. Okay, but yeah, the idea is pretty much the same. Okay, and this was the basic steps. These are the key terminologies that you need to know, right, which will be used again and again inside Banker's algorithm, right? The entire Banker's algorithm basically has two things inside it. Using these four terms only, you are going to use the safety algorithm or work on the safety algorithm. And secondly, you are going to work on the resource request algorithm. Both of these algorithm basically makes the backbone of the Banker's algorithm. Okay, so what we'll do is in this video, I think we've taken enough overview to have the right building blocks for the next video. In the next video, we'll directly jump on the Banker's algorithm, and this video we actually take a good amount of overview of what exactly is deadlock avoidance, how do we understand that idea, what is the correct meaning and the explanation of safe state and unsafe states, right? And moving on to that, we also understood what is Banker algorithm, where Banker algorithm is basically used for, and what exactly would be a very high level overview in how Banker algorithms takes care of resource allocation and deadlock avoidance. Okay, and after that, I think we took two important terminologies which make sense in real life as well. If you're requesting something more than what you had earlier claimed to ask for, then it's wrong. You have to set error. And if also you're requesting something, right, that is less than what is actually available, then it's good. Otherwise, again, you need to set a process wherein you have to wait over here. And only if these two conditions are satisfied, a successful resource allocation can take place. Okay, and then we talked about four data structures: available, max, allocation, and need. And now we have the right context to get started with safety algorithm, and after that resource request algorithm in the next video. So stay tuned. This is just the starting of Banker's algorithm. In next video, we are actually going to get a little hands-on and talk about this idea in great detail. I'll see you all. Thank you.